Wow. Okay, you really weren't kidding about a deep dive, huh? This research you sent over is, well, it's a lot.
Yeah, there's definitely a lot to unpack here.
But that's what we're here for, right? To break down all these complex physics concepts and make them a little less intimidating.
Exactly. We'll be going back to the basics, talking about units and dimensions and even those tricky vectors everyone seems to struggle with.
Sometimes I think physics is kind of like a secret code. Once you learn the language, the whole universe starts making sense.
I like that. And luckily, I've got a pretty good decoder ring ready to dive in.
Absolutely. Where do we even start with all this?
Well, I think a good place to begin is with those fundamental building blocks, physical quantities and units.
Okay, so we measure things all the time, but what's the difference between, say, a fundamental quantity and a derived one?
Okay, imagine you're building a house.
All right, I'm picturing it.
You've got your basic materials, right?
Yeah.
Bricks, wood, concrete, that sort of thing.
Right, the essentials.
Well, those are your fundamental quantities, the basic ingredients of measurement. Things like length, mass, time. They exist on their own and can't really be broken down further.
Okay, so they're kind of like the prime numbers of physics.
Yep.
Indivisible building blocks.
Exactly. Now, when you start combining these fundamental quantities, that's where you get your derived quantities.
So those are like, what, the rooms in our house? Built from those basic materials in different ways.
Exactly. Speed, for instance, is a derived quantity. It's distance, which is a length divided by time.
I see. So if the fundamental quantities are the ingredients in a cake recipe, the derived quantities are the cake itself, the delicious result of combining those ingredients.
That's a great analogy. Now, of course, to measure these quantities, we need a system of units,
Yeah.
a standard way to quantify things so we can all be on the same page.
Right, like if I said a piece of string is 5 long, you'd be like, 5 what? 5 inches, 5 centimeters, 5 football fields. The units give it context.
Exactly. And just like there are different languages, we have different systems of units for describing the physical world. The most common is the metric system.
Okay, that's the one I'm most familiar with. Meters, kilograms, seconds.
That's the MKS system, but there's also the CGS system using centimeters, grams, and seconds.
Right, right. And I vaguely remember something about an FPS system too, right? Feet, pounds, seconds.
You got it. But here's the thing. The numerical value might change depending on the unit system, but the underlying physical meaning stays the same. It's like baking the same cake using teaspoons instead of cups. You'll get a tiny cake, but it's still a cake.
A very tiny cake, but a cake nonetheless.
Exactly. But where things start to get really interesting is when we talk about dimensions.
Ooh, dimensions. Okay, I'll admit, that's always sounded a bit mysterious to me. Like a secret code for understanding the universe or something.
I like that. And in a way, you're right. Dimensions are like a hidden language that helps us understand and check the validity of physical equations. They categorize physical quantities based on their fundamental makeup.
So you're saying I can spot an error in an equation without even knowing what it means?
In a way, yes. It's called the principle of dimensional homogeneity. It basically says that the dimensions on both sides of an equation have got to be consistent. You can't add, say, a length to a mass. They're fundamentally different category.
Right, like you can't add apples and oranges.
Exactly. But it's more than just checking equations. You can use it to convert between different unit systems.
Oh, so that's how those conversions work.
And even to figure out relationships between different physical quantities.
Wait, you're telling me we can find hidden connections just by looking at their dimensions?
Let me show you. Think of a simple pendulum.
Okay, I'm picturing it. The swinging bob. Yeah.
Now, let's say we want to figure out how the period of the pendulum, the time for one full swing, is related to its length, the mass of the bob, and the acceleration due to gravity.
Right, so many factors.
Now, we could go through a bunch of complicated equations, but dimensional analysis lets us sneak up on the answer. We start by assuming a general relationship like, okay, the period, t, is proportional to some power of the length, L, some power of the mass, m, and some power of the acceleration due to gravity, g.
So like t is proportional to L to the power of something times m to the power of something else and so on.
Exactly. Then we look at the dimensions of each quantity. Time is, time. Length is length, mass is mass. But acceleration is a bit trickier.
Because it's the rate of change of velocity, and velocity is the rate of change of position.
Right. So acceleration boils down to length divided by time squared. Now we just substitute these dimensions into our equation, and we get this kind of dimensional equation.
And we solve for the powers.
Exactly. We make sure the dimensions on both sides match up, and that gives us a set of equations to solve for the powers.
That's amazing. So we can find the relationship between all these factors just by, like, playing with the dimensions.
It's a powerful tool, and it's not just theoretical. Engineers use it to design airplanes, architects for bridges, even movie makers use it for special effects.
It's like a secret decoder ring for the universe. But okay, I gotta ask, are there any limits to this dimensional magic?
Well, it can't tell us about dimensionless constants, and it only really works for equations where things are multiplied or divided, not like trigonometric functions or logarithms.
So no magic wand, but still a pretty awesome tool.
Hmm.
So where do we go from here with our newfound appreciation for dimensions?
I think it's time we equip ourselves with some essential math tools, the building blocks we need to understand more complex physics concepts.
Like a physics toolbox. And, so many people get intimidated by the math, but it really is just a set of tools, right?
Yeah.
And like any good craftsperson, the right tools make all the difference.
Exactly. We'll need to talk about things like quadratic equations and those ever-useful trigonometric ratios.
Ah, yes. SOHCHATOA. Never thought I'd hear that again after high school.
And those are just the start. We'll also touch on approximations, logarithms, determinants, geometry.
Okay, so we're building up a solid foundation here, ready to tackle anything physics throws at us.
And with that, we'll be well equipped to explore the world of vectors. You know, those arrows with a sense of purpose.
I'm ready to dive into the vectorverse.
All right, welcome back to the deep dive. Last time we were talking about dimensions, and well, now it's time to jump into the vectorverse.
Vectors, I remember those from, well, from everywhere in physics. They're like arrows, right? But why? Why are they so important?
You got it. They're arrows. And they're important because they have both magnitude, like a size, and direction. So they're perfect for describing things like force or velocity or displacement, where just knowing how big something is isn't enough. You got to know where it's pointing to.
Okay, yeah, that makes sense. Like, if I say I walked 5 meters, that's just a distance. But if I say I walked 5 meters east, well, now we're talking vectors.
Exactly. And that little addition of direction changes everything in physics. But before we start, throwing these vectors around, let's get some vocab straight. We have parallel vectors, those point in the same direction, and anti-parallel, those are opposites, and then there's the angle between vectors.
Okay, so a little crash course in Vector Lingo 101.
Now, one of the coolest things you can do is add vectors. Let's say you walk 3 meters east and then 4 meters north. Your final displacement isn't 7 meters, is it?
No way.
Yeah.
Because I didn't walk 7 meters in a straight line. I changed direction.
Right. It'd actually be 5 meters at, about 53 degrees north of east, and that's your vector sum. We can find that using what we call the parallelogram law or the triangle law of vector addition. They're kind of visual ways to combine the size and direction.
So it's not just adding the numbers, it's like following a path on a map. That's a good way to put it.
And then we have vector subtraction. Sounds scary, but it's just adding the negative of a vector.
So like reverse the arrow.
Exactly. Keep the length, but flip the direction. And that's super important for analyzing motion, like projectile motion or even like planets orbiting.
Okay. Starting to see the bigger picture here.
Yeah.
Now, can we multiply vectors too?
We can, but it's a little, well, there are a couple of ways. We can multiply a vector by a scalar, just a regular number. Think about driving a car. You press on the gas, you're increasing the magnitude of your velocity vector, multiplying by a positive scalar. Hit the brakes, you're multiplying by a negative scalar.
Oh, so you're like stretching or shrinking the arrow.
Exactly. But then things get interesting when we multiply two vectors together. We have the dot product and the cross product. Dot product gives you a scalar, cross product gives you another vector.
Wait, so multiplying two vectors can give you two different kinds of answers. My brain's starting to hurt.
I know, it's a lot to take in, but both are super important. The dot product, think of it like how much two vectors overlap in direction. Like if you're pushing a box across the floor.
Okay, got the visual.
The force you use and the box's movement, those are both vectors. The dot product tells you how much of your force is actually going into moving the box forward.
So like if I'm pushing at an angle, only part of my effort is actually doing the work.
Exactly. The dot product picks that part out. Okay, now for the cross product. This one's a little trippy. It gives you a new vector, and this new vector is perpendicular to both the original ones.
Perpendicular, so like at a right angle.
Yep. Like, imagine using a wrench to loosen a bolt. Your force on the wrench and the distance from the bolt to your hand, those are vectors. Their cross product gives you the torque, the twisting force that's loosening it.
So cross product is all about, like, turning forces. Got it.
Mm.
So we've got addition, subtraction, scalar multiplication, dot product, cross product. Are we done with vectors yet?
Almost. Next up, we're going to learn how to break down vectors into their components and see why unit vectors are so useful.
All right, welcome back to the deep dive. We've been through dimensions, vectors, all sorts of physics goodness. My brain is definitely feeling a little full, but in a good way.
That's what we like to hear. But we're not quite done yet. We still need to talk about breaking down vectors into their components and those handy little things called unit vectors.
Components and unit vectors. Okay, I'm going to be honest, those always sounded a little intimidating back in school.
Don't worry, it's not as bad as it seems.
Yeah.
Remember that walk we talked about? 3 meters east, then 4 meters north.
Yeah, the 5-meter displacement at that weird angle.
Right. Well, those individual parts, the 3 meters east and 4 meters north, those are the components of that final displacement vector. Like, they're the building blocks of the bigger vector.
So we're taking that 5-meter vector and kind of splitting it up into like a purely east part and a purely north part.
Exactly. And this is super useful because it lets us look at motion, forces, all that stuff in multiple dimensions.
Okay, I'm starting to see why that would be helpful, but how do we actually, find those components?
This is where our good friend trigonometry comes in. Imagine shining a light on that 5-meter vector at an angle. The shadow on the ground, that's like your horizontal component, the x component, and the shadow on a wall, that'd be your vertical component, the y component.
So the length of those shadows are like the size of each component.
You got it. And good old SOHCAH-TOA helps us calculate those lengths using the angle of the vector.
Trigonometry always coming back to haunt me. But are these components, are they vectors too?
They are. They have size and direction, and that's where unit vectors come in.
All right, unit vector time. What are they exactly, and why do we need them?
Think of them like the compass directions of vectors. They have a size of 1, and they point along a specific axis. So like north, south, east, west, up, down, that sort of thing.
Okay, so they're like signposts telling us which way to go in each dimension.
Exactly. And we use these special symbols for them, A and co for the x, y, and z axes. And the best part, we can write any vector as a combination of these unit vectors.
Wait, really?
Yep. Remember those components? We can write them as multiples of the unit vector. So like that 3 meters east, that would be 3a. 4 meters north would be 4.
So the unit vector is like the direction, and the number in front tells us how far to go in that direction.
Exactly. It's like coordinates for vectors.
Yeah.
And it makes adding vectors way easier. Like if you had another displacement, say 2 meters west.
Which would be what, -2a?
Yep. To find the total, you just add the matching components. So much easier than trying to picture it with arrows every time.
Wow, okay. Unit vectors, they're kind of genius.
They're essential for all sorts of things. Projectile motion, forces, electric fields, magnetic fields, you name it.
It's amazing how, like, all this math comes together to help us understand the physical world.
That's the beauty of physics, really. It's like peeling back the layers of reality and finding this beautiful, elegant structure underneath.
Well, I have to say, this deep dive has been, well, it's been a journey. But I actually feel like I get this stuff now.
I'm glad to hear it. And hey, this is just the beginning. There's a whole universe of amazing physics out there to explore.
You're right. And a huge thanks to you, our listener, for sending in this research and sparking this whole conversation. Keep those questions coming, and we'll be back to dive into something new.